Welcome back to Basic Electronics. In this lecture, we will look at the general representation of an amplifier. We will discuss the parameters which can be used to characterize an amplifier. We will then calculate these parameters for the common emitter amplifier which we have seen earlier. Finally, we will look at a common emitter amplifier configuration in which the emitter resistance is partially bypassed. Okay, let us begin. Let us now consider a general representation of an amplifier as shown in this figure. So this box here represents the amplifier. This is the source side and this is the load side. The source is represented by a voltage source in series with a source resistance Rs, and the load is a load resistance RL. So the amplifier is represented by a voltage gain AV over here, and this subscript V stands for voltage. It's a voltage to voltage amplifier. An input resistance Rin as shown here, and an output resistance Ro, that one. So this Vi here is the voltage that appears on the input side of the amplifier. If this is Vi, then this voltage controlled voltage source produces a voltage which is AV times Vi. Now this AV times Vi does not quite appear across the load, and what appears across the load will be determined by the value of this output resistance. And for a voltage to voltage amplifier, a large Rin and a small Ro are desirable, and it is easy to see why. We want all of this input voltage to appear across the amplifier, and that will happen if Rin is large, ideally infinity. What about the output side? We want all of this voltage AV times Vi to appear across the load, and that will happen if Ro is small, ideally 0. And that is why we say that for a voltage to voltage amplifier, a large Rin and a small Ro are desirable. Here is a very important point. The above representation involves AC or signal quantities only. That is, it describes the AC equivalent circuit of the amplifier. So all of these quantities, this voltage Vs, this voltage Vi, this AV times Vi, and this output voltage Vo, are all signal quantities or AC quantities. They are not the bias quantities. So is the DC bias important at all? It is, and that is because the DC bias of the circuit can affect parameter values in the AC equivalent circuit, such as AV, Rin and Ro. For example, for the common emitter amplifier, we saw that the voltage gain was proportional to Gm, the transconductance of the BJT, and Gm was given by IC by Vt, where IC is the DC or bias value of the collector current. So although the bias values are not shown explicitly in this diagram here, they are implicitly involved in these parameter values. Alright, now suppose that we are given an amplifier as a black box, this box here, and we don't know what is inside that box, and we want to find these parameters AV, Rin and Ro. The question we should ask is, what experiments would give us this information? And let us look at that in the next slide, taking these one by one: the voltage gain, the input resistance and the output resistance. Let's look at the voltage gain first. If RL is infinite, that is if this load resistance is replaced with an open circuit, then obviously this load current IL would be 0. Then there would be no voltage drop across Ro, and this Vo would be equal to AV times VI. So that suggests the following method to obtain AV. So remove RL, replace it with an open circuit, measure VI and VO, measure this voltage at the input of the amplifier, measure VO, and then AV is given by VO divided by VI. As simple as that. What about the input resistance of the amplifier, Rin? That's easy. We measure this voltage here at the input of the amplifier, that is VI. We measure this current going into the amplifier, it's called II, and then we see that Rin must be VI divided by II, and that is what it says over here. What about the output resistance, RO? There are two ways of getting the output resistance. One, let Vs be 0, that means we short circuit the input voltage source. When we do that, this Vi would become 0, and therefore AV times Vi would also become 0, and this voltage controlled voltage source then gets replaced with a short circuit. And now we connect a test source VO as shown here and measure this current IO. And now obviously VO divided by IO will give us RO. So this method works well on paper. So if we know the circuit of a given amplifier, we can look at it, we can use this method. But it's difficult to use it experimentally. And that brings us to the second method, seen in the next slide. Here is the second method. In this method, what we do is keep the voltage source, the input voltage source, and keep it constant throughout the procedure. So we don't make any changes on the input side, so Vi remains constant. And then we look at VO. So what is VO? It is RL divided by RO plus RL times AV times Vi. Simple voltage division, and that is what this equation says. Now if we make RL equal to infinity, that is an open circuit, then the voltage is going to be simply AV times Vi, because there is no voltage drop here. Let's call that value as VO1. So VO1 is AV times Vi, and that corresponds to RL equal to infinity. If RL is made equal to RO, if these two are exactly equal, then what is VO? VO is going to be simply AV Vi divided by 2, because the voltage will split equally between these two. That we will call as VO2. So that is half AV Vi, and that is equal to half VO1, because VO1 is already AV Vi. So these equations suggest the following procedure. Measure VO1 with RL equal to infinity. So that is what we get. What is RL equal to infinity? That is RL removed. So we have removed RL, measured VO, we have called that VO1. Now put it back, put the resistance back, put a pot over there and vary the load resistance, and measure VO. And when VO becomes equal to VO1 by 2, we measure that particular value of RL. And we have to actually remove RL from the circuit and then measure it. Otherwise, we don't know what exactly is being measured. And then RO is the same as the measured resistance RL. And this procedure is indeed useful in the lab when we are given an amplifier and we want to measure the output resistance. Let us now find the voltage gain AV, the input resistance Rin, and output resistance Ro for the common emitter amplifier. First we draw the small signal equivalent circuit or the AC equivalent circuit as we have done before, and now we proceed with AV, Rin and Ro. What is AV? AV, as we have seen in the last few slides, is VO divided by VI with RL equal to infinity. So we remove this RL, measure VO, and then VO divided by VI is AV. VI in this case is the same as VS. And what is VO? VO is minus GM times RC, because RL is not there anymore. So AV is minus GM times RC divided by VI, and VBE, this voltage, is the same as VI, and therefore these two cancel and we get minus GM times RC. So that turns out to be minus 42.5 millimos, which we have computed earlier for this particular example, times 3.6 K, that is RC. That turns out to be 153. So that is the voltage gain when there is no load resistance connected, or when RL is equal to infinity. What about the input resistance of the amplifier? In this case we can get it by inspection. We look into this port and what do we see? We see R1, R2 and Rpi all coming in parallel. So that is what it is. Rin is R1 parallel R2 parallel Rpi. Rpi is beta over Gm. Beta is 100 in this example. Gm is 42.5 millisiemens. So that comes to 2.35 K, and that gives us an input resistance of 1 K using this expression here. Let's now find the output resistance, and we will use method 1 that we have seen previously. And what is method 1? What we do is deactivate this input voltage source. That means we replace it with a short circuit, and then we look from the output port. Let us do that. When we make Vs equal to 0, this Vi becomes 0, that is VBE becomes 0, Gm times VBE becomes 0, so this current is 0, it's an open circuit, and then what we see from this port is simply RC. So the output resistance of the common emitter amplifier is simply RC, that is 3.6 K in this case. So now we have a complete description of the common emitter amplifier. We have AV, the voltage gain, Rin, the input resistance, and Ro, the output resistance. We now consider the common emitter amplifier with partial bypass, and let us see what this means. This circuit looks very similar to the common emitter amplifier. R1, R2, RC, CB, CC, all of these things were there in the common emitter amplifier circuit. What is different here is that the emitter resistance has been split into two, RE1 and RE2. If you recall, in the common emitter amplifier, there was Re here and there was no resistance here, and that entire Re was bypassed by this bypass capacitor Ce. Now what we are doing is we are bypassing only part of the emitter resistance, that is we are bypassing only Re2 and not Re1, and that is why this circuit is called the common emitter amplifier with partial bypass. For DC computation, Ce is open, all capacitors are open circuits. So what do we get? So this is an open circuit. We get Re1 plus Re2 going to ground from the emitter, and if we call RE1 plus RE2 as RE, then this is the circuit we get, and this is the same circuit as we had for the common emitter amplifier. So the DC analysis is therefore identical to our earlier common emitter amplifier with RE equal to RE1 plus RE2. We don't need to do it again. But bypassing a part of RE as opposed to all of it, like here, does have an impact on the voltage gain, and that we will see in the next slide. Let us now get the gain of the common emitter amplifier with partial bypass. And to do that, we first need to get the AC circuit. So we begin by assuming that at the frequency of operation, the large capacitances CB, CC and CE can be replaced by short circuits, as we did in the common emitter amplifier case. And the small capacitances, the BJT parasitic capacitances, C pi and C mu, by open circuits. So then let us see what the circuit reduces to. Here is the base. From the base, we have R2 going to ground. This is a short circuit, so then we have Vs here, then the other end going to ground. And then we have R1, and this end of R1 is also going to ground because our VCC, since it's a DC source, is now replaced with a short circuit. So that is what we have here as well, R1, R2 and Vs. And then between the base, collector and emitter, of course, we have the transistor model, the pi model. From the emitter, we have RE1 and then we have the short circuit. So we have RE1 going to ground. That is what we have here as well. From the collector, we have RC going to ground again. And this is a short circuit, so we also have RL going to ground. And the same thing here, RC and RL going to ground. The gain is given by the voltage at this node, the output node, divided by the input voltage. And we are of course talking only of the signal voltage now, not the DC voltages. And where is the output voltage in this AC circuit? This is the collector, and in the AC circuit, the collector and this output node are actually the same because the coupling capacitor is a short circuit. So we then want to get the ratio of this voltage at the collector and Vs. So let us see how to do that. Let us write an equation for the source voltage Vs, that is equal to this voltage drop plus that voltage drop. This is R pi times IB, and that is RE1 times beta plus 1 IB, which is the same as the emitter current. So we have Vs equal to IB times R pi plus beta plus 1 IB times RE1, and that gives us IB. What about the output voltage? The output voltage is the voltage at the collector node, and this current here is beta times IB, and so that beta times IB is going through this parallel combination of RC and RL. So therefore this voltage drop is beta IB times RC parallel RL, but because the current is going in that direction, it will come with a negative sign. And that is what we have over here. VO is minus beta IB times RC parallel RL. And now we can take the ratio of these two quantities to get the gain. VO over Vs is minus beta RC parallel RL divided by all of that, R pi plus beta plus 1 times RE1. Now in many situations, this magnified RE1, magnified by a factor of beta plus 1, would generally be larger than R pi, and in that case we can ignore this r pi. And again, if beta is reasonably large, like 100, this will be 100 divided by 101, which we can say is nearly 1, and we end up with the gain equal to minus RC parallel RL divided by RE1. And typically this will turn out to be smaller than the gain of the common emitter amplifier. Let's note that RE1 has not appeared as RE1, but it has appeared as RE1 times beta plus 1 in these expressions. So even if RE1 is small, say 100 ohms or 0.1 K, when it gets multiplied by this factor, such as 101 for example, we will get 101 times 0.1 or something like 10K. So even if RE1 is small, it gets magnified here because of the beta plus 1 factor. Let us make one very important point about the common emitter amplifier with partial bypass. Let's look at this ratio VBE over Vs. What is VBE? It's this voltage between the base and the emitter, and that is R pi times IB. What is Vs? We have already seen that in the last slide. It's R pi times IB plus beta plus 1 IB times RE1. So that is what we get for that ratio, and IB is common here, so we get R pi divided by R pi plus RE times beta plus 1. And why is this ratio important? Let us see. The small signal condition, namely VBE much smaller than VT, now implies the following. And let us see where this comes from. We have VBE equal to Vs times this factor, and therefore if VBE has to be much smaller than VT, that means Vs times this factor must be much smaller than VT, or taking this to the other side, we require the magnitude of Vs to be much smaller than VT times R pi plus RE times beta plus 1 divided by R pi. Now this factor is generally much larger compared to 1, therefore this whole expression here is much larger than Vt. And let us compare this small signal condition for the common emitter amplifier with partial bypass with the small signal condition required for the common emitter amplifier, and that is the magnitude of Vs must be much smaller than Vt. Now let us take a specific example. Let us say our Vm, that is the amplitude of Vs, is 20 millivolts. Now 20 millivolts is not small compared to Vt, which is about 25 millivolts, and therefore that kind of amplitude is surely going to give us distortion in the common emitter amplifier. Now let us say that this factor is 10. That means this entire expression is 25 millivolts times 10 or 250 millivolts. So the condition required in this case, that is the common emitter amplifier with partial bypass, is that the input amplitude must be smaller than 250 millivolts. Now in the example that we just considered, that is Vm equal to 20 millivolts, we have 20 millivolts on this side and we have 250 millivolts on this side. Clearly 20 millivolts is small compared to 250 millivolts, and therefore we are not going to see any distortion. So in summary, although the gain is reduced, partial emitter bypass allows larger input voltages to be applied without causing distortion in the output voltage. So that is an important benefit of this configuration. To summarize, we have learnt how to characterize a general amplifier in terms of the gain, input resistance and output resistance. We illustrated these ideas with our earlier common emitter amplifier example. Finally, we looked at another amplifier configuration, namely common emitter amplifier with partially bypassed emitter resistance. In the next class, we will start our discussion of op-amp circuits. Until then, goodbye.